We will continue our lectures on adaptive control, and this time we will talk about self-tuning control, which is an alternative approach to model reference control. I guess it is waste of time to talk which approach is better. They both have a right to exist, and basically it is a matter of taste and experience of a practicing control engineer which approach should be utilized. Well, the need for self-tuning control is exactly the same as the need for model reference control. We do face incomplete information on the controlled process, and it happens to poorly known process dynamics, to parameter drift caused by the normal wear of the system components, parameter drift caused by hardware failures. Battlefield damage is a very good example of the need for self-tuning control. Noise in the information channels takes place, and because of this, as a consequence of incomplete information, we use our best knowledge of the controlled plant. We build a control system that performs perfectly in the simulation environment. But as you apply this control law, these parameters of the control law to a real process, the system does not perform as it was required. In the self-tuning control, the underlying concept is that we observe operation of the control plant, maybe with the system, a control system that we developed. The operation is far from being perfect, but as we observe this operation, we accumulate additional information about the properties of the control plant, about the performance of our control system, and we use this information to improve the system performance, improve the control law. How to accumulate this information? Well, obviously, it cannot be done explicitly. It's not about recording data and creating an ever-increasing data array that could be processed with ever-increasing numerical difficulties, but we do it utilizing approaches known as system identification. And in self-tuning control, we use system identification for two purposes, for two basic applications: explicit or indirect self-tuning, and implicit or direct self-tuning. But in addition, there are techniques known as the online parameter optimization. I want you to take a look at the diagram that features an indirect self-tuning approach. First of all, note that we have a controlled process, and perhaps our information about this process is incomplete. This is the control effort applied to the process, and this is the system response or the controlled variable. What we do, we continuously monitor input and output data on this control process, specifically the control effort and the output of the process. We accumulate a significant data array, and first we use this data array to build so-called initial model, or base model. But in the when the system already is designed and underperforms, we use this input-output data for online parameter estimation or online updating of the parameters of the model. And as we update parameters of the model, let's say the transfer function of the plant, or matrix A, matrix B, matrix C of the control plant, we're getting improved information. And we use this improved information to redesign system controller. How often system controller could be redesigned? With all this computing power we have, it could be done reasonably frequent. Obviously, we cannot redesign the controller with the same frequency as a discrete time control law is being applied. But we can always have a procedure for updating the control law, for improving the control law that operates with some time step, maybe once a second, for example, maybe 10 times per second, which is acceptable in many technical systems. And what I see here, the updating of the controller is operational. The result of this updating is or are improved, updated parameters of the controller. But as far as controller is concerned, it operates like in the 361 first control class. It picks up the output and creates the control law. And the purpose of the control law is to make sure that the reference and the value of the system output are very, very close. And this approach demonstrates, or this diagram demonstrates, the implicit or direct self-tuning scheme. Why do we call it implicit? Because take a look at the previous drawing. Here we obtain characteristics, transfer function, or state variable definition of the controlled plant in the most explicit form. Matrix A, matrix B, matrix C, or parameters of the numerator of the transfer function, parameters of the denominator of the transfer function. We use this data to redesign the controller. But when it comes to the implicit approach, in the implicit approach, we do not have the explicit definition of matrix A, fundamental matrix of the controlled process. We do not have the matrix B explicitly defined. What we're getting during the implicit control procedure, directly we're getting the changed parameters of the control law. So we're skipping over some explicit operations targeting the transfer function of the control plant, or state variable definition of the control plant. We go directly after the parameters of the control law here, and parameters are immediately implemented in the controller, and controller operates as a controller supposed to operate. So I would say word direct is a good word in application to this approach, because we are affecting parameters of the controller directly, not by first estimating properties of the control plant and then redesigning the controller and then changing parameters of the controller. Self-tuning scheme. But in addition to self-tuning, there is an approach, and this approach is a valuable approach, and this approach is a usable approach, online parameter optimization. This is the control plant. This is the controller. And the system operates. But as the system operates, we should be able to observe the error and the output, and if necessary the control law, the reference signal, and what we're getting out of it is some kind of criterion of the goodness of the operation of this control system. Example of such a criteria is error squared times time integrated, or integral of error squared time type of criterion. This criterion would be minimized if system performs perfectly. If system's performance is imperfect, this criterion will have increased values. Now, this criterion obviously depends on the parameters of the controller, and we do have numerical optimization procedures that could reshuffle parameters of the controller, variate parameters of the controller in such a way that the criterion would be driven to its minimum, and therefore our control system would operate as good as it possibly can operate. Following the way the course is outlined, we will be talking now about the system identification problem. System identification problem is formulated as follows. We do have online measurements of the system input and the system output. The system input could be a set of variables that we can consider as vector x, and these variables are applied to the particular process, and they affect the performance, the output variables of this process. The output variables could be, again, considered as a vector because there could be more than one output variable, and they are driven by the input variables, and we symbolize them by vector y. They both are functions of time. And then we have to utilize our best knowledge of the physical phenomena behind the process operation, and we have to suggest a configuration for a mathematical model of this process. So this model could be defined as an output variable, but don't be confused. It is the output variable of the model. Generally speaking, it could be quite different from the output variable of the real plant. We can also call it the calculated output, because we do not observe it, we compute this variable. And this output variable of the model is represented by a vector y model. It is also a function of time, and there is some kind of mathematical configuration. I call it operator f, and in this operator we have set of parameters symbolized by variable a and the input variables of the process. So how this model operates? The input are functions of time. We can observe these inputs. And in addition, we have parameters of the model. And if inputs change, if parameters change, the output of the model also will change. So, if we would have some model configuration, then we should be able to utilize accumulated data to estimate parameters A of this operator. And how we want to do it? We have to consider error. Error is the difference between the observed output of the process and the calculated output or output of the model. They both are functions of time, therefore error is function of time, but minimization of instant value of this error is meaningless. What we want to do, we want to come up with some kind of criterion that would describe operation of our model not in the particular moment of time, but over a sufficiently long period of time. It is a criterion. We call this criterion Q. It is normally a function of the error, of this error. But error depends on the model definition. And the model definition contains parameters, A. Therefore, this criterion, in addition to be a function of error, it's also a function of parameters A. And this is what we can do. We can minimize this criterion with respect to parameters A. And moreover, if we would consider criterion describing operation of our model over a long period of time, sufficiently long period of time, then basically effect of time will not be seen. You will see only criterion of the goodness of the model defined as a function of parameters of the model. And then, of course, it would be a conventional minimization problem. Now we will follow the approach. The approach implies that we have to perform step number 1, the definition of the base model. And this is a step that is performed offline. To perform this step, first we have to obtain an array of measurements of the input vector x and the output vector x. And I want you to take a look at the timing that I am using here. X is a function of I times delta t, which means that we have here discrete values of variables x. X is a vector. And I is the discrete time index. Delta t is a constant step. And therefore, I guess we even don't have to mention this delta t. We can technically call this x of I, assuming that we're dealing with x for 1 times delta t, 2 times delta t, and so on. Now, the total number of points, of measurement points should be large, much greater than 1. I wouldn't be surprised if we will be working with 1,000 points. Could be more. The same is true about the output vector. It is discretized in time. I is the discrete time index. And of course, values of x and y should be taken synchronously for I equal 1, for I equal 2, and so on, so forth. Then it is time to assume some best guess model configuration. You have to have some exposure to the nature of the process. You have to understand the physical phenomena behind the process operation, but the model should be defined as follows. The output of the model as a function of time, it is some function f of parameters and observed input vector. After the model configuration is defined, we're performing section C. We have to estimate parameters A by minimizing the criterion. What kind of criterion we normally would use? The criterion most commonly used is known as sum of squares. Take a look at this expression. This criterion is function of errors or discrepancies between the model and the real process output. It is basically chosen such that it would be function of parameters. And it is defined as this sum. Under the summation, first of all, we perform summation from I equal 1 till I equal to n where n is a sufficiently large number. If n is sufficiently large number, then criterion Q would practically depend only on the parameters of the model. Now take a look at the summation sign. On the summation sign, first of all, you see the discretized value of the output of the real process. It's right here. Then you can see the calculated output of the model, and it is calculated for parameter values equal to A and for the input vector x, and this x is synchronized with the output y. The difference obviously is the modeling error calculated for time equal to I times delta t. It's an immediate value of the modeling error. But then what we do, we perform summation. And we perform summation of the squared errors. So this is why the approach is known as the sum of squares. Now, you understand that if we would minimize the criterion Q with respect to A, we're supposed to get parameters of the model. But not just parameters, but parameters that would minimize the discrepancy between the model and the output of the real process. So parameters will be obtained at some point, and then there is a special, rather statistical by nature, task to prove or to demonstrate that the model that we obtained is statistically significant. And it's a special issue. It may or may not be considered in this course, but as a practicing engineers, you should be looking into not only getting the model, but also into proving that this model is statistically significant, and maybe it could be simplified without the loss of statistical significance. Now let's take a look at the step number 2. Step number 2 implies that we have to perform online updating of the base model. And what we do, we actually update parameters of the model using some recursive procedure. Recursive means step-by-step procedure. It also could be called iterative procedure, performed iteration by iteration. But the word iteration implies that we make our system better and better. Perhaps we are. So you can call it recursive procedure, you can call it iterative procedure, but the procedure normally looks like this. This is the new set of parameters of the model obtained at the step or iteration number j. It is equal to the old set of parameters of the model obtained at the previous iteration. And then we have to add the correction. And this correction is some kind of function w of the old parameter values, newly observed output, newly observed input, and this procedure has to be performed on a step-by-step basis. First for 0, j is equal to 0. This is for the base model. Then you have to do it for j equal to 1, 3, and so on. And as a matter of fact, if you have a self-tuning system, this procedure could be working on the continuous basis. Well, I put clarification here saying that A of j actually is set of parameters A for time equal to j times delta t. I want to make a note that the purpose of the step number 2 is to address the incompleteness of information of the controlled process. You know, when we got our base model, for the base model, we, no matter how many observations we used, we still were dealing with limited size of data arrays. Whether this size was sufficient or insufficient, it is not clear from the very beginning. And then in addition, a real process can exhibit parameter drift, which means that the set of parameters of the model obtained at this particular time, let's say 11:45 in the morning, may not be good, may not be applicable at 2 afternoon. So this is the reason for continuous updating of the parameters of the model using some iterative process. Now, it is also good to keep in mind that in the parameter estimation task, there are two subtasks. They could be performed both of them or only one of them: parameter estimation and parameter tracking. Parameter estimation is a typical process for building the base model on the data array that is fixed, closed data array. Parameter tracking may be used to address parameter drift in the continuously changing environment. And for parameter tracking, we use special modifications of the iterative procedures. And at this point, I am ready to discuss with you the least squares method, with all its numerical implementations and the various aspects of its implementation. First of all, I want to tell you that there is a true process. And if we would look into the mathematical description of the true process, probably known only to God Almighty, we would say that the output of the process is defined in this particular linear situation as some vector of parameters multiplied by the vector of input variables. We are assuming that the process has one output and m inputs. I guess this vector alpha should be transposed. In this case, we would surely get the scalar by multiplying alpha by x. Here are components of vector x listed: x1 as a function of time, x2 as a function of time, and so on. And the last one is xm as a function of time. The output is also a function of time because it depends on the input and parameters alpha. This is the simplest case. We have here a linear process, or process that has linear properties. Again, the true configuration of the process description is not known to us. First, what we will do, we would discretize and consider discretized input variables of the process and the output variables of the output variable of the process. So we're assuming that there are several inputs, x1, x2, xm, and one output. And as I said, this is the scalar description of the relationship or expected relationship between parameters of the model, input variables of the model, and parameters of the process, input variables of the process, and the output of the process. I want to emphasize that for parameters of the process, I use alphas. Later, I will be using A's for estimated parameters of the process. Time, T is continuous time, and here we have set of parameters that we are assuming at this point are time independent. And we are assuming that parameters alpha are unknown coefficients that we want to estimate. If we would successfully estimate these parameters, we would be able to get a very accurate model representing this relationship, which is not known to us. Now, first of all, in order to do the estimation, as I said, we have to perform synchronous sampling of the input and output variables, and this would result in the following data arrays. And we're assuming that the sampling time step is constant, and it does not make any sense to write this delta t again, and again. So listen, what capital X is? Capital X right here is the vector that has all discretized numerical values of input variables of the process. And all these variables are recorded at time equal, let's say, 1 times delta t, 2 times delta t, and so on. So why do I have transpose sign here? Because the way I built array is this. The first row represents vector x of input variables recorded at time 1 times delta t. Second row represents the vector of input variables, transposed actually, recorded at time or measured at time equal 2 times delta t, and so on. And I have, supposed to have, a very huge array of these measurements. I wouldn't be surprised if you would have 1,000, 2,000, 10,000 measurements in this array. Capital N is the total number of measurements in this array. I call this array, capital X with letter N as a subscript. This letter N supposed to remind you that we're dealing here not with one set of measurements, but with the total of N sets of measurements, and they are recorded in this fashion. Similar situation we have for array yn with capital letter N as a subscript implies that we have a huge column of measurements y taken at time equal to 1 times delta t, output y measured at time equal to 2 times delta t, and so on. As I said, since delta t is the same, it doesn't make any sense to write it again and again, and I can conveniently call it y1, y2, yk, and so on. As I said, k is the discrete time index. N is much, much greater, not just 1, N is much, much greater than M. M is the total number of inputs. Now, what do we know about the least square method solution? Least square method solution provides, generally speaking, unbiased results. It gives you results that are optimal, assuming that we use this available to us data. But it's also good to remember that least square method does not result in the true coefficients. The least square method produces only estimates of these coefficients, and I intentionally do not call them alpha. I call them AN. What is the significance of this subscript N? I want to emphasize that these coefficients are obtained using these data arrays, array X and array Y, and each array contains total of capital N measurements. And therefore, the solution that I will get out of this data supposed to be will be dependent on the total number of observations. If I would use additional, let's say, 200 observations, the result could easily be different. And what you can see now is the traditional, conventional, known to everybody solution of the method, least square method. To obtain unknown coefficients A, I have to take array xn transposed times xn. What is the result of this product? Result of this product is a square matrix, which is M times M matrix. M times M matrix. Because X transposed is M times N, X is N times M, the result is a square matrix. We invert the square matrix and we multiply it by a column that has total of M elements. M, not N. The column has Xn array transposed. Xn array is M times capital N. Y is capital N times 1. We multiply it, we're getting a column. And unsurprisingly, we're getting here a column of unknown coefficients. But I want to emphasize, they're not unknown coefficients, they are estimates of unknown coefficients. All right. However, least square method offers the following promise, that if total number of observations would approach infinity, then vector of estimates will become equal to the vector of true coefficients. This is the property of the least square method approach, known as being unbiased. So LSM provides unbiased estimates of unknown coefficients. And also from this expression, you should realize that the more measurements we use, the more accurate estimates we would extract, under one condition: if parameters of the plant do not exhibit drift. But in my initial discussion of the least square method, I'm assuming that parameters are constant. The next, what I would like to talk to you about the effect of measurement noise. We are engineers. We understand that in real life, whatever measurements we perform, we're facing measurement noise. The sources of noise are many. The inaccuracy of the instrumentation that we use, various effects of weather, and so on. So don't expect that variables x1, x2, x3 and variable output, variable y are recorded as they are. No, noise is added to these variables. Now, we always talk about the noise, and I guess the word noise has two flavors. You know, generally speaking, if we would have difficulty estimating some parameters, a mathematician or statistician would tell you, listen, why don't you try to inject the noise in the system input? And I guess properly injected noise would enhance our accuracy of our estimation process. At the same time, the noise has a different meaning, and I want you to be very clear about this reality of life. I put together a drawing. The drawing features the process. And for simplicity, I assumed two input variables, x1 and x2, and one output variable y. I want you to take a look at two signals, V1 and V2. They are injected into the input of the system. The signals will be added to x1 and x2, and these inputs, V1 and V2, will surely result in additional variability of the output of the process y. You can call them noise. By their statistical properties, it could be white noise or Gaussian noise, but one way or another, they will result in the increased variability of the output of the process y, and they will enhance the estimation process. But at the same time, I want you to realize that these input signals, x1 and x2, including this noise component or not including this noise component, are measured and recorded. And when they are measured, it is possible that additional noise components have nothing to do with this noise will be added and will go directly into the recording. But what is special, these noise components have nothing to do, they do not affect the output of the process whatsoever. These noise components are those that make estimation process less accurate. And this is what I want to address right now. Now, if you record the output of the process, and if noise is injected in the output, the record of the output will contain component of noise, and of course, it may not be good for the estimation process. So this is the noise. This noise and this noise that makes estimation less accurate, and this is what we have to be concerned about. When it comes to noise in the measurement channels, this noise and this noise in the measurement channels is a good definition of this noise. It does not affect the process. It exists only in the measurement channels. This noise is supposed to have we have to make some assumptions about this noise. Fortunately, these assumptions are acceptable in most practical situations. They are realistic assumptions. Assumption number one is that noise is additive. So this noise is added to the true signals. Multiplicative noise is a very difficult thing to deal with, but additive noise is something that we can consider and, most important, can handle. The second issue is this: noise is unbiased. In other words, it has zero mean value, which means that the instrumentation that we use should be very carefully calibrated. If it's not carefully calibrated, the measurements will have always some bias. However, with proper calibration, we can achieve a situation when if right now we have value slightly greater than the true value. A little bit later, the value that comes out of our monitoring system will be a little bit lower than the true value. In other words, the zero mean value for noise is expected. Then there is issue about finite variance for noise. Obviously, in most realistic situations, noise has low variance than the signal. However, it never overshadows the signal, because in this case, the monitoring task would be a very difficult task. And then there is a statement like this: noise is not correlated with input and output signals, and I will give you more information about this. And there is no correlation between noise in the input-output channels. What is implied? The implication is this. Look, I'm trying to compute covariance element describing the relationship between X in the channel number J and Y in the channel number J. Y is the noise. So if I would add together products of X times Y, and the result will be divided by the total number of observations, we're supposed to get zero. We're getting zero because there is no relationship between X and Y, and also because Y has zero mean value. But the zero could be observed only for very large numbers, N for very large number of observations. Issue number 2. If I would compute the correlation coefficient between two components of noise in channel number I and noise in channel number J, I will get zero, providing that number of observations is sufficiently large and I is not equal to J. Here what I have, I compute covariance coefficient between the output Y and the measurement noise lambda in the output channel. Again, it is expected that this covariance coefficient will be zero, providing that the number of observations is sufficiently large. And finally, if I would consider noise in any of the components of the input vector and noise in the output, they are uncorrelated, and therefore this product is zero, providing again that the number of measurements is high, and it will work for every input channel I equal 1, 2, 3, and n. You know, and I would also say it is useful to say exactly the same thing, but using matrix vector form. In the matrix vector format, I will take this huge array X, n. If you remember, n is the total number of rows in this array. It is transposed, and I will multiply it by array gamma, capital Gamma. Capital Gamma is the array of components of noise discretized, and I have all these components of noise from time equal to 1 till time equal to n, and also from time channel number 1 and channel number m. Well, this product is a square matrix filled with zeros, period. It's a m by m matrix because this term is m times n. Because it is transposed, this one is n times m. The result is a zero matrix filled with zeros. Let's take a look at this, which is more interesting situation. I have huge matrix gamma. It contains all components of noise recorded for time equal 1, time equal 2, time equal capital N times delta T, of course. And it's multiplied by exactly the same thing, but not transposed. The result of this multiplication is a square matrix. And the square matrix is a diagonal matrix. All the soft diagonal terms are zeros because component of noise in channel 1 does not is uncorrelated with component of noise in channel 2. So this is why this element is 0. However, if I will be working on this product, I would find out that along the diagonal of this matrix, I would have variances of noise into channel 1, channel 2, channel 3, and so on. And this happens if n approaches infinity. And the notation that I'm using, sigma k squared, is the variance of noise in channel number k. And then, of course, these two expressions are very easy to explain. It is product of array y times array lambda that represents noise in the output channel. It is 0, and this is array gamma that represents noise in the input channels, multiplied by array lambda that represents noise in the output channel. This product is also 0. These properties will help us very soon, and you will appreciate these expressions. First of all, let's consider the effect of noise in the output of the parameter estimation process, in the output y of the process. What does it mean having noise in the output, additive noise? You can always assume that instead of having column yn, we have column yn plus lambda n. So lambda n represents a component of noise at time 1, at time 2, at time 3, and so on. And therefore, if I would write down expression for the least square method procedure, this one, I would have to state that instead of output yn, I have yn plus lambda n. So the whole result will be this. Now, I can always place 1 over n inside of this expression. Here 1 over n is in the power of minus 1. Here 1 over n is in the power of 1. So obviously 1 over n cancels this 1 over n, and you don't have to worry about. Let's assume that n approaches infinity, is very large. What will happen? What will happen is this. Coefficients A will not change. They will be exactly the same as they would be without noise in the output. Why? You can take another look at these properties and these properties. And therefore, the following conclusion should be drawn. Noise in the output does not result in biased estimates of the parameters A. However, I told you that this will hold, or certain terms will become zeros only if n is a large number. Therefore, if we are concerned about the accuracy of our estimates, n should be processed, should be increased, because purpose of n is averaging the effect of noise. We have to increase number of observations to average out noise in the system. And now we can consider effect of noise in the input channels of the process. So let's assume that noise is additive noise, and because of this, instead of xn array that contains all measurements of all input variables, we have xn plus gn, plus gamma n, it's gamma, capital gamma. And this capital gamma represents components of noise at any time in every input channel. So this is what we have instead of xn. And let's go back to the equation of the least square method. I'm working on this equation, and I also take advantage of the fact that with a large value of n, there is no correlation between noise and input signals results in this product equal to 0. No correlation. If I would change the order of this multiplication, I still will have no correlation, and I still will get 0 for this matrix. If I would consider the fact that there is no correlation between input noise and the output, this product will be 0 if n is sufficiently large. So what's left? This term, even if n approaches infinity, will never disappear. It will be equal to this. It's a square matrix. It's a diagonal matrix, and all diagonal elements are equal to the variance of noise in the channel number 1 and the channel number 2 and so on. Therefore, since even if n approaches infinity, this term does not disappear, we should conclude that measurement noise in the input channel results in biased estimates of parameter A, regardless of the number of observations n. Now, let's try to assess the bias. Let's say that we do have noise in the input channels. What is the price we're paying for this reality of life? Well, look what we do. Here I have the explicit definition of the least square method formula that defines parameters A, or estimates of the parameters A of the process. What will happen if you have noise? You looked at the analysis that I presented earlier. In the case of noise, we will get estimates A tilde that will be equal to 1 over n xn transpose xn plus this matrix that does not disappear. Then, of course, we have to invert it. Then we have to multiply it by x transpose times y. But this term will cause the bias. Now, let's see what we can do about this. So first of all, let's assume that when we use xn transpose times xn, due to the noise, we in actuality getting this expression. I would love to record x without noise, but noise is there. I do not have x without noise. And therefore, when I calculate this xn transpose times xn, I'm getting actually this expression where noise is present. With one additional fact, the noise cannot be seen as clearly as it could be seen in this formula. So, what could we do about this? You know, if I know that input contains noise, and also if I know the variances of this noise, where variances could come from, obviously effect of a storm with lightning on our measurements could not be quantified. However, every piece of instrumentation, every sensory equipment comes with the suggested accuracy. So for every piece of machinery, for every piece of monitoring system, we have these sigmas squared. They come from the manufacturer. And therefore, assume that I am calculating parameters A. I have in reality this expression within this square brackets. Let me subtract the covariance matrix of noise. I know it's a diagonal matrix. I told you that I'm assuming that I know this individual sigmas. So this could be done. And then if we would continue our calculations, what we will get will be still not the true A, not the true alpha values, but we would get parameters of the mathematical model. We will get enhanced A's if we would make this type of correction. Finally, I want to talk about the effect of cross-correlation of input variables. You know, let's say we have these variables x1, x2, and x3. Who knows if they are cross-correlated? In the worst-case scenario, it could be that xi for some input channel I is almost equal to c times xj plus d. Very clear bias in monitoring variables of the control plant. What if this happens? If something like this will be happening, two rows of matrix xn transposed xn will be quite similar. They will not be linearly independent any longer. Now, when in a matrix we have two columns that are linearly dependent, or two rows that are linearly dependent, you can realize that the matrix will become singular. You cannot invert a matrix like this. Therefore, the cross correlation will result in the determinant of the matrix xn transposed xn to be almost zero. This situation is known as a poorly defined parameter estimation problem. An almost singular matrix would present a serious numerical difficulty for calculation of unknown coefficients. In addition, since x is almost the same as y, there will be significant confusion in the parameter estimation problem, in the configuration of the model. Do we really have to include both x and xi and xj if xi and xj are linearly dependent? It's a special discussion that we would be investing time later. And especially this issue is important for introduction to process control course, where we extensively use mathematical models.